Hey, let's go ahead and get started. So, welcome everyone to our weekly Planet AI webinar, our weather webinar, where we talk about the factors that impact our weather over the next couple quarters. And today, what we're going to be talking about specifically is the science of long-range weather forecasts and how they're awesome, how they're less awesome, and how to interpret all of this when it comes to financial decision making. So, before I get started, just to introduce myself. So, my name is Dr. Hansi Singh. I am one of the founders of Planet AI. I am an Earth Systems scientist. I used to be a fellow at the US Department of Energy, and I am formerly a professor. Myself and my co-founder, we decided to start this company because we were really tired of seeing a lot of insights that sort of stayed within research circles and didn't make it out into the real world. And especially when these insights potentially could be really groundbreaking for helping folks in the real world make decisions as our planet changes, gets warmer, the weather gets more volatile, etc. So, let's talk about long range forecasting, which is what we specialize in at Planet and where it can be really useful and where potentially you want to be really careful using it. So I'll begin by first talking about the science of weather forecasting, and then I'll go into how we extend that predictability from that 7-day weather forecast into much longer time horizons, from weeks to months to potentially years. And this is through something that we call Earth system modeling, which I'll tell you more about. Then I'll talk about what we can predict with long range forecasts and what we can't. And then I'll go into some specific recommendations for your decision making. So, to start, we have to jump into the science. So let's talk about weather prediction. So this is the weather prediction problem in general, right? What we would like to know is based on some initial state, say what we can observe today of how the weather looks, can we use physics to determine after a certain number of days what the weather is going to look like? And our answer to this within weather forecasting specifically has been to use what we call numerical weather prediction models. So let's jump right into those models. So, numerical weather prediction models are atmosphere only models. That means that they only model the atmosphere. And these models are very complex because the atmosphere is very complex. The atmosphere moves, there's a ton of light moving through it at all different wavelengths. It has all of these teeny tiny particles in it. It has a lot of chemical constituents. It sometimes, gets unhappy and gets stormy. It behaves differently if you're near the surface and near the stratosphere versus kind of in the middle of the atmosphere. All of these things add to the complexity. So these models are hundreds of equations, tens of thousands of lines of code. And all together, they are then used to predict weather. And one thing that makes these models pretty complex already is, of course, we live on a planet and these equations, you actually have to solve them at every single grid cell that you create on your planet or within your domain. So it just really adds to sort of the computational complexity. So all of these models, we run them on supercomputers. So even though, I call this like, oh, it's atmosphere only, there's a lot to the atmosphere, and these are very complex. So the way that we use these models to predict the weather is that we initialize, meaning that this is that starting state, the initial state that we talked about. Um, we initialize these models with observations. Then we run the models, and using those runs of that model, we produce our 10-day forecast. And when we run the model, we run many different realizations. And this is what I'm going to get into because this is where things get really messy when it comes to forecasting. So the reality is unfortunately, we can't come to a single answer of what the future is going to be. I wish that I could just be like, I am certain that this future is going to happen, and unfortunately, physics says nope. And so let's think about that for a second and why that is. So, any initial state of the atmosphere has some uncertainty to it. So, at some point, we stop being able to kind of look, at fine enough granularity. And so, because we can't look quite at that granularity, we end up with some uncertainty. And so, that uncertainty is shown in this kind of little circle here. And so, what that means is that within this uncertainty, if we start and run our weather model, from any of these particular initial conditions within this sort of range of uncertainty, we will get a different answer. And so that is the uncertainty of our forecast. And so when we finally then create the final forecast, this forecast is probabilistic. And so what that means is that, even if you're looking at the weather tomorrow or even this afternoon, it'll tell you this is the probability of rain, and it will give you some sort of percentage associated with that. And so weather forecasts are fundamentally probabilistic, and it has to do with the fact that these forecasts are spreading out as we kind of predict further and further forward in time. And the reason why these forecasts spread out is because of chaos. So you've heard probably of chaos theory, the butterfly effect. Um, the more sort of kind of scientific way that we think about this is that when we start the atmosphere at two very similar states, maybe states that are so similar that they only differ by how a butterfly wing flaps, so similar states. After about 2 weeks, these two states, if I run my weather model, they will have diverged exponentially from each other. And so, what this means is that the atmosphere is only predictable up to about 14 days. And so, this is why your weather app is not going to tell you information usually beyond that 14 days, or really ever beyond that 14 days, because fundamentally we are limited by the physics of the atmosphere, and the atmosphere is extremely sensitive to initial conditions, and the forecast will spread. So, how do we get around this? Like, if there was no way around this, then we would just all go home right now and we'd say, okay, well, we can't do anything. But luckily, that is not the case. And that is because the Earth system is actually predictable over a range of time horizons. So this includes not only the atmosphere, which has, days of memory up to a couple weeks, but also the land surface, which has weeks to months of memory, the ice, which has months to years of memory, and the ocean, which has years to decades to centuries of memory. In fact, the deep ocean has millennia of memory. You can predict this thing for a long, long, long time. So these are the components of the Earth system that we need to incorporate to do anything beyond that 7 or 14-day weather window. And so, what does that look like in the modeling world? That looks like an Earth system model. An Earth system model is a much more comprehensive framework for thinking about how the Earth system and the weather evolve. So, it includes not just that complex atmosphere model that we talked about earlier, but it also includes a three-dimensional ocean model. So we model how the ocean moves and changes, heats up, cools down, radiates. That is included. We also include the land. We include ice. And all of these components, they sort of talk to each other and vary with each other through this kind of mathematical framework that we call the coupler. And this form of modeling has been so important for how we understand the Earth system and forwarding the science that it actually won the Nobel Prize in 2021. So Dr. Suki Manabe, who you see right here, who has been at GFDL forever, I actually had the pleasure of meeting him when I was a graduate student. And so he really started running these models in the 70s that were these fully coupled models. In other words, they include all of these different components of the atmosphere system, or sorry, of the Earth system. And in particular, of course, our modeling has gotten so much better since he first started doing this. So back in the day, they were running these on uh, machines where you'd have Fortran punch cards and things like that. Now, what we have are literally thousands of equations, millions of lines of code. Some examples of these types of models include CESM, the Community Earth System model, as well as, for example, the UK ESM, which is run at the Met Office, Hadley Centre in Britain. So there are major modeling centers that have these types of models around the world. And these models are used for many things, including Earth system predictability beyond that 7 to 10 day weather window. So, how do we run these types of models? The way that we run these types of models is actually very similar to a weather model, but it's just, more complicated. So, first of all, we initialize these models with, for example, not just initial conditions from the atmosphere, but also conditions from the ocean, so we can figure out how the ocean will evolve with elements of the land surface, including quantities like soil moisture, for example, also the ice. We initialize this model or these models, and then put all of this within this Earth system model and use this to generate the many different possible realizations of what the forecast is going to be over the next weeks, months, and even further into the future. It's really important to remember that basically any time that you want to be beyond that, 7 days, 10 days, 14 days in terms of prediction, you have to use this more complex modeling framework. And unfortunately, yeah, with greater complexity comes more scientific uncertainty, comes, a lot more computational resources needed every time you need to run these models. Yeah, there are definite cons. But on the other hand, in order to basically predict anything from weeks to months to, decades, long-term climate, all of these require Earth system models. We cannot do them with atmosphere only models. So this has really been sort of the breakthrough that we've seen over the last few decades. Really being able to utilize this more comprehensive modeling framework and using that be able to predict the Earth system over these much longer timescales than are possible with your numerical weather models. So I'll first then want to talk a little bit about the practicalities of this. So great that, we have this cool tool in our toolbox. Now, what can we use it for? And I think that's really important because obviously, like, you don't want to try to chop down a tree with a drill, right? You want to use the axe. And so you really want to make sure that you're using these models for the right thing. So, what is long range weather forecasting really good at predicting? So, what it's really good at predicting are these major modes of variability within the Earth system. So, these modes of variability, the thing you might have heard the most about that everyone talks about is El Nino. El Nino, La Nina, known as ENSO. And yeah, that provides a great amount of predictability in the climate system. We can predict this thing out up to a year, and we can use that then to tell us some really important insights into how our weather is going to evolve. There is a whole nother alphabet soup worth of different modes of variability that exist. These include the MJO, which I have talked about a lot at these webinars. These include the QBO, the NAO, the IOD, et cetera, et cetera. The other thing we've talked about a lot too are persistent ocean temperature anomalies, and these can really, drive weather. And so, how do these drive weather? These really drive the weather through teleconnections because these patterns then create these large scale atmosphere and ocean waves. And these types of waves then connect these patterns to weather around the world. They impact temperature, precipitation, winds, humidity, solar radiation over many different parts of the world. And so the really important thing to note, if you want to make sure that you use the axe to cut down the tree, is that when these types of modes of variability are strong, teleconnections are robust, and we are able to predict things really well, right? So this is just fundamental. Now, this year, right? I think you might have, if you've come to some of these earlier webinars, you might have heard me, talking about El Nino and La Nina and just being like, oh, we don't have that for predicting this year because we really don't. It's very weak. But guess what? We have some other great things. So we have the QBO, which is in a great phase to really kind of amp up the MJO. And the MJO has some beautiful cross-Pacific teleconnections that really help us predict well subseasonally. And so, really, if you don't have one thing, you have other things. We have this huge blob that's sitting in the North Pacific. And so we use all of these elements to really help us get a handle on what that long range outlook looks like. So when the modes of variability are strong, the teleconnections are robust, and things can be very predictable over these long time horizons, weeks and months into the future. Where and when are these long range predictions most reliable? So I want to give some rules of thumb here. So, first of all, let's talk about the tropics. In the tropics in general, temperature and precipitation are actually pretty reliable year round. Yeah, it's tropics are very predictable. Now, unfortunately, the extratropics are much less predictable. Temperature is much more predictable than precipitation. And in general, in the extratropics, the winter is the most predictable. And then that's followed sort of by the shoulder seasons. And the summer can be sort of less predictable, though it sort of depends on the phenomena here. But just remember, winter is the most predictable. And then we have sort of everything else. And sometimes we have really good windows of opportunity. And sometimes we're just like, we don't know what's going to happen. So these are some good rules of thumb to remember when we think about that predictability. Then, when it comes to precipitation, I did mention that in the extratropics, precipitation isn't great. Well, there's places where in the extratropics, precipitation can be predicted with some skill. And I have circled these here. And so, in general, these regions are regions that are linked to the jet stream. And so, in general, if the jet stream and its movements have an impact on precipitation over that region, then we tend to have some good subseasonal and seasonal predictability. And this is because the jet stream in general is more predictable than, say, a thunderstorm. Thunderstorms are very, very hard when they're sitting in like Alberta or in Iowa or somewhere in Mongolia. But on the other hand, when we have these sort of large scale patterns of precipitation near the coast that are linked to the jet stream, we have some predictability there. So, one thing I want to say is that in general, we tend to do really well at forecasting when a lot of predictive factors converge. So, an example of this, which I mentioned a couple of weeks ago, is sort of this forecast that we put out about precipitation over South Asia. And we talked about how in late September and early October, there was likely to be a lot of rainfall. And in fact, that turned out to be true. Unfortunately, yeah, there was some pretty intense rainfall over the region. And it turns out that at that time, that forecast was a really robust forecast because we were able to combine the fact that the Tibetan Plateau was warm. We were right at the time of the late season monsoon, and the MJO was in its phase two. And all of those factors together sort of meant that our forecast that there was going to be a deluge over South Asia did indeed happen. And so, sometimes with these windows of opportunity where all of these factors are converging, we can sometimes get extremely good forecasts. And this is one example. So you might be wondering, now that I've talked about deluges, are extreme weather forecasts any good? And these sort of depend when it comes to long range forecasting. Droughts and arid conditions that are conducive to wildfire, because these are cumulative, they tend to be reasonable. Extreme rainfall in the tropics, especially within these windows of opportunity, we can do quite well with those. This is because rainfall in the tropics is determined by sort of large scale weather patterns and energy transfers, and those are quite predictable. Heat waves are also predictable because they sort of depend on the land surface. And so, if we use things like soil moisture and vegetation for predicting those, we can tend to get some good insights on those a few weeks in advance. Cold snaps linked to the stratosphere are predictable, as we've talked about in a few webinars ago. And we can predict the severity of the hurricane and the typhoon season. Now, let's get to areas that we cannot predict. So, thunderstorms far away from the tropics, these are very, very, very hard to predict. So, usually we do not have more than a day, sometimes hours, to really get a good sense of where these are going to form. And related to that are hail and tornadoes, which are linked to those thunderstorms. Extreme wind events, yeah, you might have about a week, maybe more of predictability, but probably not that much more than that, though you could put together sort of a risk estimate, perhaps, with greater lead time. Monsoon onset can be hard sometimes, and this is not because the tropics aren't predictable. It's actually because we have a lot of aerosols in the air due to tailpipes and industrial pollution, and those can really impact when the monsoon starts. So even if you get all of the conditions right, if the aerosols are a little bit unexpected, then that can really affect when the monsoon starts. And we tend to have less of an issue with this later in the season because all of those aerosols have sort of been washed out of the atmosphere. So, definitely for monsoon starts, this can be a challenge. And then finally, the location of hurricane and typhoon landfall can be a challenge as well. So, it's important to keep in mind like, we can't really feasibly do that more than, a week in advance once that hurricane or typhoon forms and we have a sense of where its pathway is going to be. And kind of coming into this, I just really want to emphasize, sort of a couple of things about where these predictions are less useful. So, where they're less useful, as I said before, is these thunderstorms. And these thunderstorms in particular are what we call mesoscale convective systems. They form not with sort of the same kind of large scale weather patterns as, for example, an atmospheric river. And so, because of that, they can be difficult to predict in the extratropics. And these tend to happen kind of in the summer season and in the shoulder seasons. So, just kind of keep that in mind, right? If a freak thunderstorm happens, yeah, it's probably not predictable more than a couple of days. And in particular, in the summer, when we have temperature anomalies that are due to thunderstorms, those are hard to predict, right? Because the thunderstorm was hard. And so, therefore, the temperature anomaly related to that thunderstorm is also going to be hard to predict. Then, in addition, it's sort of important to remember that over different time horizons, we do have some, limitations. So we really don't want to provide weekly forecasts beyond, say, 6 weeks. We just don't have insights to be able to really provide you with that weekly resolution beyond that 6 week time frame. And then usually for monthly forecasts, usually we do not provide them beyond 5 months. And so when we get to beyond 5 months, all forecasts tend to be seasonal, and those seasonal forecasts do have skill. But yeah, we don't really have that same kind of month to month temporal resolution when we go beyond 5 months. So these are just important limitations to keep in mind. This is science. I wish that, it could be magical, but it's not. It has limitations. And so, a couple of final things when we're thinking about making decisions from this data. In many applications, it's really important to remember that weather conditions are most important when they fall outside a range or they're beyond some threshold. So let's take plant growth or shopper behavior. Plants like to grow within kind of a narrow temperature and, amount of rainfall. And when we're outside of that, right, then plant growth is going to suffer in some way. Same way with shopper behavior. Shoppers love to go shopping when it rains. But if there's too much rain and their streets flooded or, it's a pain to get to the, mall, then they're not going to go shopping. And so there's really this kind of like, happy area where it's raining just enough that everyone wants to go shopping, right? So these are the kinds of things that it's really important to think about when you're thinking about weather conditions and how it affects your decision making, that there sometimes can be these ranges and thresholds. In terms of thresholds, for example, think about natural gas supply. If your temperature is below a certain threshold, then yeah, like that is going to really, impact production, for example. Or think about ports. If winds are over a certain number of knots, or if you have over a certain amount of precipitation, then that's when that port is going to close. But anything below that, it'll function normally. And so, these things aren't linear. They have these kind of non-linear and threshold behaviors. Furthermore, when it comes to making decisions, and this is my sort of final slide here, it's really important to remember that forecasts are probabilistic. And so this is where sometimes a near normal forecast can sort of lead to some confusion. A near normal forecast doesn't necessarily mean normal conditions. You really have to look at the probability distribution. If that probability distribution looks like the climatology, then that means that basically anything can happen. It means that we don't really have good insight on any details of what to expect. On the other hand, if that forecast distribution, is sort of like very sort of geared towards that normal, like it's very focused towards that normal, that can give you a bit more insight on like, okay, we're expecting pretty normal conditions. So it's really important for your operational decision making when you see a normal forecast to not be like, okay, it's going to be normal, I'm done. It's really important to say sometimes those forecasts actually mean that anything potentially could happen, and there's not really that much prediction possible within the long range forecast to really kind of narrow that range of possibility. And so, hopefully, I have not confused everyone more than they need to be confused about long range forecasting and what it can be used for and what it shouldn't be used for. And so, I'm happy to take any questions. I'm happy actually to just hang out for a little bit longer because we have just about reached the end of our time here. And just really quick, announcing our next week's webinar, which is really in particular about how climate change affects weather patterns as our planet warms and why it is important for your decision making. Thank you so much. I'll be here to answer questions. Okay, I see a question here and in the chat, and it's about AI and machine learning, and whether AI and machine learning will sort of continue to improve our ability to forecast long range. So, yeah, this is a great question, and the answer is complicated. So, first of all, it's really important to remember, right, that AI and machine learning have really changed weather forecasting. So, numerical weather forecasting in particular has sort of really been given a run for its money with AI weather forecasting over this kind of 7, 10, 14-day time horizon. And this is because there's a really good amount of sort of quasi observational data to train on. And, our models are very good at training on these, finding patterns, and then using them to, kind of predict the future based on the current initial condition, essentially the weather forecasting problem. The big issue here is that as soon as we get to anything kind of beyond that 7-day or 14-day weather window, we literally do not have enough data to be able to train a model. When I say enough data, we don't have enough observational data. So what that means is that then we start to have to rely on physics-based models. these physics-based models are these Earth system models, and we need to rely on huge amounts of data sets that are produced by these types of models. And so what that means is that your AI model in general is probably not going to be hugely better at what it does than the physics-based model because it is literally based on that physics-based model itself in order to get the training data. And so because of that, I think that we really have seen some kinds of limitations in terms of what we can expect in terms of how AI can improve some of this forecasting. I will say that AI is great because it's so fast, right? We can run these models so much more quickly. And it's great also because often it can learn patterns that potentially, me or you as humans may not be able to see, right? So I think that those are areas where definitely there's a lot of promise with AI, but unfortunately, I don't think we're going to see the same kind of just like rapid scale improvement in forecasting ability that we have seen just with the 7-day weather forecast in terms of those types of AI weather models. I see a couple more questions. So the first one is forecast data available to user provided both point level as well as graphically? Yes. So any good forecast should provide both an expectation value at every location for what we expect the forecast to be. And in addition, we also provide a probability distribution. So that's where like that bell curve type, illustration comes in. In general, for example, I do have a slide on this. These are the kinds of probability distributions that we provide if you query at any given location. Okay, thank you. Thank you for that question, Jan. Stephen has a question. Do your models account for the possibility of disruption in the AMOC? So, in fact, we have seen within our forecasts, and I will hit on this particularly next week at our webinar, because disruptions in the AMOC are something that we suspect may be in the pipeline as we go forward. And so what we do see is, for example, this kind of cold, warm, or cooling hole, cold anomaly over the North Atlantic. And we think that may be related to the dynamics of the AMOC. So, yeah, we kind of keep those types of things in mind when we evaluate forecasts. And just to be clear, like the models that we run, because they have a full ocean, these are the same models that also, when we run them much longer term with, different quantities of atmospheric CO2 and other forcing agents, that we do see AMOC collapse. So these are one and the same models. So I guess the short answer would be yes, like we would be able to see those kinds of things, though no, I don't expect that to happen over the next month. I think that's pretty important to state that we don't expect catastrophic things to happen with the AMOC, but we do expect it to be affected as our climate warms. Um, okay, so Ruthu has a question about combining the physics-based models with the forecasting models. So all of these models are one and the same. The physics models are what we use within forecasting. And once again, right, as I said, we can train AI emulators to sort of do some of this physics as well. And they are very cheap to run, and we can sort of combine all of these things together to produce the final forecast. But absolutely, like the forecasting is done through fundamentally the physics models. And our understanding of the physics models or understanding of the physics is fundamentally going to determine how well our models are able to forecast, which is why it's just so critical that we continue to really develop the physics going forward so that we can forecast better. You're welcome, Ritu. Well, thank you all so much. I really enjoyed these questions and feel free to contact me if you have more questions. Happy to hop on a call, talk about the long range forecast, talk about the long range outlook, and yeah, hear about potentially areas where you think this could be useful for what you do. So, thank you all.